Hello, and welcome to this problem-solving video regarding the Coulomb force. In this video, we're going to return to this question that we posed earlier in earlier videos about what is responsible for that centripetal force in an atom that keeps an electron in orbit around the proton. And basically what we're going to do is we're going to prove that it is not gravity, but rather the Coulomb force which is responsible. So we'll need to compute both the gravitational force and the Coulomb force, and hopefully find that the Coulomb force is actually much, much larger than the gravitational force that is acting between a proton and an electron. So in order to do that, let's refresh our memories. Gravitational force, the magnitude anyway, is given by gmm on r squared, while for the Coulomb force, it is our constant k times q1, q2 on r squared. So the product of the charges divided by their separation squared multiplied by this constant k. And let's remind ourselves of some constants, and then basically let's just go ahead and plug those in and see what we can calculate. So because I'm doing this here, I'm just going to be rounding some stuff. So the first thing I'll do is I'll define that g is actually just going to be, say 7 times 10 to the negative 11. We'll go ahead and define k as just 9 times 10 to the 9. Okay, we can do that the mass of the proton is basically 2 times 10 to the negative 27. And the mass of the electron, and we'll just leave it at 9 times 10 to the minus 31. And the charges we'll also just call, so in terms of magnitude anyway, they're the same. And we'll just call them, again, 2 times 10 to the negative 19th coulombs. Okay, so that's what we're going to use instead of these exact values over here. So if we make these nice rounding substitutions, then we can calculate the force of gravity is just going to be the 7 times 10 to the negative 11 times our masses, so times 2, and I'll just collect the numbers and then put some powers in the back, minus 27 and 10 to the minus 31. And that's all divided by r squared. You notice I haven't looked up a value for r squared. That's okay, because it's going to appear in our other expression as well. So actually the comparison between the gravitational force and the electric force is true at all distances. So let's just go ahead and do the other one. So that's the 9. And now I'll collect all the numbers this time. So our q's are 2 and 2. And then all the powers. So there was a 10 to the 9th from the k. There's a 10 to the minus 19 from one charge, and a 10 to the minus 19 from another charge. And again, all on r squared. So then we can go ahead and start simplifying. So fg, well, we were supposed to do a 7 times a 2 times a 9. Sure, let's do the 2 times 9. That's 18, which is basically 20. Then times 7, we can go ahead and keep that as 140. We can collect all of our times 10 to the stuffs. When you're multiplying the same base to different powers, you just add the powers. So we have negative 11, negative 27, and negative 31. So if we add these two, for instance, that's negative 58, negative 69, divided by r squared. Whereas the Coulomb force, we've got 4 times 9, so 36, times 2 sets of negative 19 would be negative 38. But then we have to add 9 to that, so that's 10 to the negative 29. And all on r squared. And then if we want to, we can go ahead and pretty this up a little bit. So that's 1.4 times 10 to the minus 67. Just bringing in the 2 powers of 10 that are hidden inside 140 and cancelling out some of our powers here. And we can do the same sort of thing. So that's 3.6 times 10 to the negative 28. And both of those, again, are on r squared. So at any arbitrary distance, we can see that there's basically almost 10 to the 40 difference between the Coulomb force and our gravitational force. So we've proven what we wanted to. The Coulomb force is much, much larger, basically a factor of 10 to the 40 larger than our gravitational force. And technically we should put some units on these. They will end up being newtons once we put our radii in meters. So, some food for thought. If the Coulomb force is always greater than the gravitational force, then why is it that we don't talk about the Coulomb force when we drop textbooks or launch cannonballs, or talk about how galaxies move around in the universe? Why is it that everyone, kind of correctly, says that on these larger scales, gravitational force dominates, when here we're saying that this result of Coulomb force being larger does not actually depend on the distance?